Hey, so let's take a look at these review stations. Yeah, we've got trig solving and trig identities here. Okay, station one. Station one says find all the solutions. Okay, so we've got in number one, 2 cosine x equals root 3. Oh, no worries, we're just going to divide both sides by 2. And so here's where that time we put into memorizing our unit circle values is going to come and help us. Remember, cosine is the x coordinate on the unit circle. And so we're saying, when is the x coordinate? Root 3 over 2. And I know of two places. One of them is at pi over 6, and the other one is at 11 pi over 6. But since we said all solutions, now we need to add plus 2 pi n to each of these. And there's our answer to number 1. Number 2, on the other hand, is very similar to number 1, but number 2 says 2 cosine 2x minus root 3 equals 0. So we're going to add the root 3, we're going to divide by 2, and we're going to get to cosine 2x equals root 3 over 2. Great. Now, remember here when we were at cosine x equals root 3 over 2? No, we're in a similar place. Cosine is still equal to root 3 over 2. Since this is all solutions, we still only need to go around once. So what are we going to have? Well, we're going to say that 2x, this is 2x, 2x equals pi over 6 plus 2 pi n, and 2x equals 11 pi over 6 plus 2 pi n. See, we're taking these answers, and they're not equal to x like they were over here. They're now equal to 2x. So when we think we're done, there's one more step. So what is it that we still need to do? Well, we need to divide everywhere by 2. And so our answers in this situation are going to be x equals pi over 12 plus pi n. And here we get x equals 11 pi over 12 plus pi n. Okie doke. Okie doke. That's station 1. Let's take a look at station 2. Station 2 is another problem that says all solutions. And problem number 1, tangent squared x minus 1 equals 0. So that's asking us when tangent squared x equals 1, because we're just going to add 1 to both sides. Remember, when you take the square root of both sides of an equation, you have to remember, what is it again? That's right, the plus or minus. So we're wondering when tangent is plus and minus 1. Now, some students have this ready, but others need me to remind them, well, remember that tangent is sine over cosine. And for our value to be 1, we need to have a number over itself. To have negative 1, either this one needs to be negative or this one needs to be negative. So where on the unit circle will we find the situation where the x and y coordinates are either, because of the plus or minus, either the same or opposites? And that happens at all the pi over 4s. So I'm going to have pi over 4 plus 2 pi n and 3 pi over 4 plus 2 pi n and 5 pi over 4 plus 2 pi n and 7 pi over 4 plus 2 pi n. But wait a minute. First of all, there's a lot of repetition here, and I think we missed something. What's the period for tangent? Remember, on the graph of tangent, we had negative pi over 2, and we had positive pi over 2. What's the period there? How far is it from here to here? Pi over 2 minus minus pi over 2. I get pi. Period is pi. So why am I adding 2 pi n if the period is only pi? Well, I shouldn't. It makes me look quaint. It makes me look. It's not cool, dude. You're wearing your grandmother's clothes. Sometimes that's a fashion statement. Other times, really. I mean, your grandmother could have had great taste. But if she didn't, no, don't do that. Okay, so here we go. Now this. Well, let's think about adding pi to this number. So this is pi over 4. So that would be 4 over 4. But wait a minute. If I add 1 pi over 4 plus 4 pi over 4, don't I get 5 pi over 4? So these two are in fact the same. And again, you know, I really could put them both down. It's not wrong. It's just overkill. It's just no. So I'm not doing that. And same thing happens here. If I add pi to this one, I get that one. All right, and this says add pi. So I get that one. So I don't need that one. Now, I'm down to these two, and that's fine. Most people are happy with that. But let's go back for a moment to our original solution. We had pi over 4 and 5 pi over 4. We had 3 pi over 4 and 7 pi over 4. Do you see it? They're all pi over 2 apart from each other. So not only are these on the same line, and therefore instead of saying plus 2 pi n plus 2 pi n, I could just pick one of them and say plus pi n. And the same thing here, from here to here, that's that pi. And I could just say that plus pi n to this one. That's what got me to these. But now I'm thinking, geez, they're all pi over 2 apart from each other. And so really, I can keep these, or pi over 4 plus pi over 2n. That's the tidiest, that's the sleekest version of our answer to station number 1. Okay? Okay. I'm sorry, problem number 1 on station 2. Problem 2 on station 2 says 2 sine squared x equals 1 minus sine x. Well, do you see the degree bigger than 1? So let's move everything to one side so we can factor. And now, you know, I want to factor this trinomial. I want to factor this trinomial like 2x squared plus x minus 1. So if we know how to factor 2x squared plus x minus 1, by whichever means you prefer, we should be able to use that same parallel structure to factor this polynomial. Well, not really a polynomial, but it has the same form. So we've got 2 sine x minus 1 equals 0, and we have sine x plus 1 equals 0. Okay, so when is sine equal to negative 1? Sine is equal to negative 1. I need some space over here. Sine x equals negative 1 when x is 3 pi over 2. But because this is all solutions still, we're going to say plus 2 pi n. Okay, now what about this one? That's saying, when is sine x equal to 1/2, right? We're going to add 1, we're going to divide by 2. Well, sine is equal to 1/2. 2 places on our unit circle, at x equals pi over 6, and x equals 5 pi over 6. But remember, this is all solutions, and so every time we go one period away in the negative direction, or, I'm sorry, in the positive direction or the negative direction, yeah, I get another solution. So I need these plus 2 pi n's. Okay, these are our solutions to problem number 2 on station 2. Let's take a look at station 3. Station 3 now comes with a restriction. Find all the solutions on 0 to 2 pi. And problem number 1 says 2 cosine squared x plus cosine x equals 0. Again, when I have this degree bigger than 1, I'm thinking about factoring. I'm pulling a cosine x out, and what's left when I take a cosine out of both of these? 2 cosine x plus 1. Remember, cosine divided by cosine is 1. It doesn't go away. If you throw it away, you've just gotten the problem wrong. Please, please, please. You're factoring, right? So you're dividing. You're dividing each of these by cosine. Cosine divided by cosine is not 0. Stop making that mistake. Okay. So we set each factor equal to 0. And we get cosine x equals, watch out, negative 1/2. Many students move this over, it stays positive. I don't know how. So when is cosine equal to 0? Well, and look, we're only looking on 0 to 2 pi. So when is cosine equal to 0? Cosine is equal to 0 because cosine is the x value at x equals pi over 2 and 3 pi over 2. But what about x equal to negative 1/2? Right, well, cosine is the x value. X's are negative in quadrants 2 and 3. And where is, do we just have a little overness? That's when x equals 2 pi over 3 or 4 pi over 3. So we've got these 4 solutions to deal with. Okay. The second problem on this station also has that restriction. 2 sine 3x plus 1 equals 0. Or sine 3x equals negative 1/2. Subtract 1, we divide by 2, we get here. Now, this is the place where that has an impact. When we have this restriction and we have this multiple angle, this tells me 2 things. How many times do I need to go around the unit circle picking up solutions, right? Think about it. This is an x transformation. It divides all the x's by 3. So when our graph used to take this much space, now when we divide this number by 3, whoa, we can now fit 3 of those graphs in there. And so instead of getting 2 solutions, 2 places where sine is equal to negative 1/2 on 0 to 2 pi, because of this, we can fit 1, 2, 3 complete versions of the graph, and every one of those complete versions has 2 solutions. So the way we do that is go around the unit circle this many times, picking up solutions. Now, the first time we go around the unit circle and say, when is sine equal to negative 1/2, we come up with 7 pi over 6 and 11 pi over 6. That's the first time around. Then the second time around, we're going to add 2 pi to each of these. And remember, since we're adding with a fraction, Mrs. Rowan, my 7th grade math teacher, says we've always got to make a common denominator. So 2 pi is going to be 12 pi over 6. So 12 pi over 6 plus 7 pi over 6, and that's going to be 19 pi over 6. And I'm going to add 2 pi as well here, and so I get 23 pi over 6. Now remember, that's the second time around. This is the first time around, this is the second time around, and now I have to add 2 pi again. So when I add 12 to this, I get 31 pi, I get 31 pi over 6, and when I add 2 pi over here, I get 35 pi over 6. Okay, but we're not done. See that? We're asked to find what x is. So now we have to divide everything by 3. And so we're going to get 7 pi over 18, 11 pi over 18, 19 pi over 18, 23 pi over 18, 31. 31 pi over 18, and finally 35 pi over 18. Good, nice. And check it out. 36 pi over 18 would be 2 pi. So we're within our 0 to 2 pi-ness. That's great. Here, this is almost 6 pi. No, we don't have to worry about that because at some point we're still going to be dividing by 3. Okay? Okay. So that was station number 3. Let's take a look at station number 4. Station number 4 features stuff. Again, with station 4, we're on 0 to 2 pi. And our first problem says tangent squared x sine x equals sine x. Now, many students, what they want to do is divide both sides by sine and get tangent squared equal to 1. Except, here's the thing. If you do that, there's a really good chance you're throwing solutions away. Yeah, so I don't want to really divide by or multiply both sides of an equation by a trig function if I can avoid it. Because that's the kind of situation that's going to throw away sine. So don't rush to that. Let's take a look and see what happens here. Now, if I'm not going to divide both sides by sine, what I am going to do is move all this stuff onto one side. And so now I have tangent squared x sine x minus sine x equals 0. Okay, I can factor out the sine x. Both terms out. I'm still left with tangent squared minus 1. I can still get tangent squared equal 1, but look, now sine equals 0. Right, because we set each factor equal to 0. So sine equals 0. Tangent squared x minus 1 equals 0. And we just saw tangent squared x equals 1 a few moments ago. And what we noticed with this was when we took the square root of both sides, and don't forget that plus and minus, when we took the square root of both sides, we ended up with all the pi over 4s. Well, all the pi over 4s. And so this would give us the answer x equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But what about over here? When is sine equal to 0? Well, remember, sine is the y value. And the y value is 0 in the unit circle. At x equals 0 and x equals pi. Hey, Mr. Duplo, why aren't you including 2 pi? Well, what does that symbol tell me? This symbol says 0 is included. This symbol says 2 pi is not included. I actually get the problem wrong if I put 2 pi there, because they told me at the very beginning of the problem I should be paying attention to that. So, here are my 6 solutions. Okay? Okay. So, let's now take a look at the second problem. So, let's get into tangent squared x minus secant squared x equals 0. This kind of reminds me of that identity secant squared minus tangent squared is 1. But I can't really use that here because of that. So, what I'm thinking about instead is rewriting. So only one trig function. And it doesn't matter if you get rid of tangent squared, it doesn't matter if you get rid of secant squared, you should end up with the same answers. How about this? If I remember, I'll go back and do it both ways for you. Let's start with getting everything in terms of tangent, because I know that, and this is from my Pythagorean identities, secant squared is tangent squared plus 1. So I can replace this with tangent squared plus 1. Remember that minus sign? Yeah, that didn't go away just because I put this stuff in there. So my problem really is to be tangent squared x minus tangent squared x plus 1. Hey, look, see, I've got to distribute that. So now I've got 2 tangent squared x minus tangent squared x minus 1 equals 0. 2 of them minus 1 of them. Hey, that's just 1 of them. And then I'm going to add 1 to both sides. And we just solved this problem again, didn't we? So we've got tangent squared x equals 1. Take the square root of both sides. Oh, please, by all the gods, make sure you remember the plus and minus. And this is where we said, remember, when are the sine and cosine values the same? Because a number divided by itself is going to be 1. A number divided by its opposite would be negative 1. And we saw that happening at x equals 1 over 4, 1 over 4, so 1 over 4, and I skipped 5 over 4. Okay. So here's the second problem of station 4. What's station 5 got in store for us? Ooh, it's not solving, it's verifying. Oh, who doesn't like a good verifying problem? So number 1 says sine x minus sine x cosine squared x equals sine to the third x. Now, please remember, this is not solving. This is verifying. And remember, with verifying, we're going to turn one side into the other. We can't do something to both sides of the equation, like divide both sides by sine. Can't do it. So what can I do? Well, I generally take the more complicated side. Generally, these problems are set up to take the left side and turn it into the right side. Not always, and you should be able to go both ways. Just generally, it's easier to take something that's more complicated and simplify it, rather than to try and take something that's been simplified and figure out how they made it this more complicated. So what I see here are 2 terms, and I see that these terms both have a sign in common. So I think about GCF factor. Okay, so pulling out a sine x. Remember, sine x divided by x, sine x is not 0. Number divided by itself is really almost always 1. And here, when I divide this expression by sine x, I have cosine squared x. All right. Now, those of you who have been working to memorize your Pythagorean identities, you should recognize 1 minus cosine squared as sine squared. And if you didn't recognize that, well, you should probably review those identities some more. And now we've got sine times sine squared. That's going to be sine to the third. This is the same thing that we saw when we did this problem last semester, right? We have a thing to the first, a thing to the second. When the bases are the same and I'm multiplying, what can I do with the powers? I can add them. 1 plus 2 gets me x to the third. And that's what I'm seeing here. And lo and behold, I'm done. All right, so how is problem number 2 any different than this? Well, on the left side, we still have 2 objects joined with subtraction. But I don't see a GCF yet. And on the other side, I don't have sine to the third, I have sine to the first. So which of our strategies do you think would be a good strategy to use here? You know, I think the idea of rewriting this with sines and cosines is probably a really smart one. Remember, cosecant is the reciprocal of sine. We've got our cosine. And remember, cotangent, that's cosine over sine. Okay, so this can be 1, because look, see, they both have a common denominator. 1 minus cosine times cosine is cosine squared. Okay, now what's 1 minus cosine squared? Yes, you really do need your Pythagorean identities. 1 minus cosine squared is sine squared. And divided by sines. So sine squared over sine, well, you know, that's the same as this. And so I can cancel one of those. And now I'm left with sine, which is in fact where I was asked to go. Excellent. How about station 6? Let's take a look at station 6. Ooh, it's got stuff. Verify. that sine theta over 1 minus cotangent theta plus cosine theta 1 minus tangent theta equals sine theta plus cosine theta. Ew. Yeah, so, you've got a couple of things you can do here. You could multiply top and bottom by the conjugate. You could make a common denominator. You could rewrite everything in terms of sines and cosines. What would be easier for you? What do you think would be the best way? And while I often think maybe I should do something like make a common denominator, or maybe I should use conjugate. I think I definitely use conjugate more than my students do. My students generally rewrite things in terms of sines and cosines. So that's a longer way. Sometimes a very long way. But, I'll humor you. It's going to be sine theta over 1 minus cosine theta over sine theta. And then over here we have this cosine theta. And we get 1 minus sine theta over cosine theta. Well, that's great. Okay, so now what do I have to do? Well, because I took this path, I've got to make a common denominator down here. We did this in complex fractions last semester. Here I need to multiply by sine over sine, and here I need to multiply by cosine over cosine. And so what am I going to have? I'm going to have sine theta over sine theta minus cosine theta all over sine theta plus cosine theta. And again, on the bottom there, we've got cosine times 1, cosine minus sine, all over cosine. All right, now what? Well, with complex fractions, I said I'm going to do that flip and multiply. So that'll take us to sine theta. Sine theta times flip, flip, flip. Many people do the multiply and forget to flip. We need to flip this. So we're going to have sine theta on top and on the bottom. Sine theta minus cosine theta. Okay. Plus, we're going to do that same thing here. We're going to flip. Please don't forget to flip this. And have cosine theta over cosine theta minus sine theta. All right, so we flipped and multiplied. How did that help? Well, let's take a look at how that helps. Now we've got here sine squared. And we've got sine minus cosine. Now we have our plus sign. And look, cosine squared theta over cosine theta minus sine theta. And now a lot of students feel stuck. Well, check it out. I want these to have a common denominator. But I don't particularly want to multiply everything over here by cosine minus sine, nor do I want to multiply everything over here by sine minus cosine. So instead what I'm going to do is say, hey, sine minus cosine, I got a sine, I got a cosine, but now the minus is here. You know what? I bet I could get this if I divided each of these by negative 1. So I'm going to factor out a negative 1. That'll become a positive, and that'll become a negative. And now I have that, and I have that. Oh, look at that. That's wonderful. Okay, so where does that take me next? Now that I have this common denominator, I can write sine squared minus cosine squared over sine theta minus cosine theta. Now, many students are tempted to say that's equal to 1, but no, it isn't. It's not sine squared plus cosine squared. It's sine squared minus cosine squared. And that's not equal to 1. Sine squared plus cosine is equal to 1. What about this? Do you see anything you could do here? Well, if you said, hey, that's a difference of squares, I could factor that. Good job, you. So we're going to have sine minus cosine times sine plus cosine. And all of that is over sine minus cosine. Well, those cancel, and I'm left with sine plus cosine. Ta-da! All right, good. So there are certainly other ways to do this. This is the long way that most students prefer. Yeah, they find that very reassuring. I don't think we're going to take the time to do the other approaches, though, I would certainly encourage you to think about with that one instead of rewriting in terms of sine and cosine. Instead of that strategy that we used, you might want to think about making a common denominator or multiply by the conjugate. Okay, good. There's station 6. Station 7. Station 7 is another verifying problem. It says cosine theta equals 1 plus sine theta plus a tangent theta equals secant theta. All right, now it's true I could make a common denominator, but that's a binomial. I really don't want to do that. Instead, I actually want to do conjugate here. Oops, 1 minus sine, not sine squared theta. Okay, why? How does that help? Well, now I have this difference of squares on the bottom, and that's going to end up being 1 minus sine squared. Here on top, don't forget, that cosine has to go to all of that. Okay, cosine theta, 1 minus sine theta. And then we've got plus tangent theta. Okay, now many students actually, when they do this, they lose the tangent. It's still there. It's still plus tangent. Don't lose the plus tangent. Okay, so what can we do? Well, I remember that 1 minus sine squared is equal to something. It's equal to cosine squared. And now I can cancel a cosine with a cosine. Okay, so I guess I'm at this place now where I can say 1 minus sine theta over cosine theta plus a tangent theta should turn out to be a secant theta. Well, I guess I have a couple of strategies. I could rewrite this with a common denominator. And so if I took that path, I'd have 1 minus sine theta plus sine theta, because this is going to be sine theta over cosine theta. That plus, okay, all over cosine theta. And then what? Well, minus sine plus sine, they cancel each other out. Now I've got 1 over cosine theta, and we know that 1 over cosine theta is secant theta, and we're done. So rewriting in terms of sines and cosines, not so bad there. I could also, with this problem, split this fraction into a couple of pieces. Remember, we can only do that when we have one object on the bottom. If I had this, yeah, I couldn't split this into 2 fractions. No, because I got 2 things on the bottom, but I only have 1 thing on the bottom. So I can say that's 1 over cosine, and minus, and then we have sine over cosine plus tangent. Well, what's sine over cosine? And for that matter, what's 1 over cosine? Well, that's secant minus sine over cosine is tangent plus another tangent. Well, minus tangent plus tangent, oh, they go away. And I'm just left with secant theta. Good. So we see lots of different ways that we could maybe get to our answer. Station 8. Some more verifying problems on it. Number 1, sine theta, 1 minus cosine theta, plus 1 minus cosine theta over sine theta. And somehow we're supposed to turn that into 2 cosecant theta. Well, again, I'm thinking about a number of things here. I'm thinking here about multiplying top and bottom by the conjugate. So I'm going to multiply up here by 1 plus cosine and 1 plus cosine down here as being one path. Another path that students like to do is to make the common denominator. And if I remember, we'll do both. Let's, well, I would definitely do the conjugate here. I know my students are going to make that common denominator, most of them anyway. So here I need to multiply by sine over sine, because that's what's over here. And while this fraction got the sine over sine from here, this fraction needs the 1 minus cosine. So I've got 1 minus cosine over sine theta. And I need to multiply by 1 minus cosine theta over 1 minus cosine theta. Okay, this is foiling. So sine times sine, sine squared. 1 minus cosine, minus times minus is plus cosine squared, all over sine theta, 1 minus cosine theta. All right, so can you make this tidier at all? Well, sure, minus cosine is minus 2 cosine. Nice. Do you see it? Do you see it? What's sine squared plus cosine squared? 1. And 1 plus 1, well, that's going to give me up top 2 minus 2 cosine theta over sine theta 1 minus cosine theta. Oh, great. Now what? Because that doesn't look like that yet. Is there anything else you can do? Well, we've condensed it down into one fraction instead of two, and that's good because we only saw one thing over here. Hey, do you see it there in the numerator? These terms both have a 2. What would happen if we factored out a 2 from each of the terms on top? 2 divided by 2 is 1, and then we have our minus, and 2 cosine theta divided by 2 is going to be cosine theta. And don't forget, all of that is over sine theta, 1 minus cosine theta. Goink, goink. 2 over sine, well, that's 2 cosecant. And we're done. You've got to know your reciprocal identities. 1 over sine is cosecant. Okay, that was the make a common denominator approach. I kind of wanna look at that other situation where I multiply top and bottom by the conjugate. Let's go back and just try it out. See how I remember it this time. Oh, weak memory, you thwart me so. Okay, so my conjugate for this, 1 plus cosine theta. 1 plus cosine theta. There's a plus there. Okay. So I'm multiplying. Actually, I'm distributing. Maybe I should resist the temptation. I do need to FOIL on the bottom. And when I FOIL on the bottom, sine theta, 1 plus cosine theta, plus 1 minus cosine theta over sine theta. Okay, so I've done the top, but now what about the bottom? Well, that's FOILing. I end up with 1 minus cosine, plus cosine, minus cosine squared. Well, these cancel. And on the bottom, because these cancel, we have 1 minus cosine squared. Okay, what is 1 minus cosine squared? From my Pythagorean identities, I know that's sine squared. Oh, cool. Look. Doink, doink. Now I have 1 plus cosine over sine. Yeah, so that's kind of sad, isn't it? Because I'm supposed to have something else. Remember, this is supposed to be equal to, oh, that was it, 2 cos, no, yes, 2 cosecant theta. So, oh my goodness, I forgot. There's a plus sign here. There's all this other stuff. Huh. Well, so I guess I could say, because these cancel, I've got 1 plus cosine theta over sine theta plus 1 minus cosine theta over sine theta. Hey, these have a common denominator. So if I write this as 1 plus cosine plus 1 minus cosine all over the common denominator of sine, what do you notice? Well, 1 plus 1 is 2. Cosine minus cosine, ooh, the cosines cancel, and over sine theta. Hey, that's the same as 2 cosecant theta. There you go. So again, I don't care. I'm not sure Justin cares. We don't care about which method you use to verify this, as long as you're doing good math, as long as you're adhering to the rules of what you can and cannot do. Now, I will say, please don't be that person who starts off, gets stuck, and then looks at the answer and says, well, in order to get here, I need this step. But there's a whole bunch of stuff in the middle missing. You know, if you don't see the stuff in the middle, we're going to find it and mark it wrong. So please, don't stop, or don't sort of work both ends. I mean, sometimes that helps people, but often it doesn't. Okay, the second problem on station 8 is secant theta sine theta minus sine theta over cosine theta, and that should give us cotangent theta. All right, what do you want to do? Do you want to turn this into 1 over cosine? That's a path. Do you want to make a common denominator? That's a path. What do you want to do? Yeah, I agree. Most students are scared of this and don't change it into something they're less scared of. Instead, they make a common denominator. And that's cool too. And here we need sine over sine. And this was a minus. Okay, so now I have this common denominator. We can write this as 1 fraction cosine theta sine theta, right? These are being multiplied here and here. And on top, I've got cosine theta secant theta minus sine times sine squared theta. Well, that's great. Now, you tried to hide from it, but guess what? You've got to turn this into 1 over cosine theta. And look, those cancel. So on top, I'm just left with 1 minus sine squared theta. And do we remember this Pythagorean? Sure, 1 minus sine squared is cosine squared. And now I can take a cosine and a cosine. Well, I'm left with cosine over cotangent, cosine over sine, and I know that that's cotangent. Okay? So look, notice, at this point, I could have rewritten, so I had 1 over cosine. But I made a common denominator instead. And now here, yeah, I still have to rewrite that. So that's my recommendation to you for problem number 2 on station 8. Station 9. Ooh, we go back to doing some solving and dropping our mouse. How awkward. Okay. Station 9. We've got solutions on 0 to 2 pi. And number 1. 2 sine x minus 1 equals 0. Oh, we saw this station before, but it was all solutions. This shouldn't be so bad for us. Now we just want the solutions on 0 to 2 pi. I know sine is the y value on the unit circle, and the y value is equal to 1/2 here and here. So what angles are we talking about? Well, we're talking about this one being pi over 6. And this one is 5 pi over 6. And those are my answers. That's it. Now, the second problem says 2 sine 3x minus 1 equals 0. Okay, I get to that same place where sine equals 1/2. But this condenses this graph of one period. I divide all those x's by 3, and now I've got this. And I can fit 3 full graphs. Okay, well, we know every time we go around the unit circle, or every time we have another period of the function, we're going to pick up 2 solutions. When is sine equal to 1/2? Well, sine is equal to 1/2 at pi over 6 and 5 pi over 6. That's our first time around. This says we need to go around 3 times. Okay, go around 3 times, picking up solutions. So if I add 2 pi to this, I get 13 pi over 6. If I add 2 pi to this, I get 17 pi over 6. If I add 2 pi to this, I get 25 pi over 6. And if I add 2 pi to this, I get 29 pi over 6. And that's way bigger than this restriction of 2 pi. But don't worry, because look, we still have to divide everywhere by 3. Oops, yeah, by 3. And 1 over 3. And these are all multiplications that I need to do. And so what are my answers going to be? Well, here I'm going to have 6 of those answers. And I'm going to have pi over 18, 5 pi over 18, 13 pi over 18, 17 pi over 18. Oh my goodness, I still haven't even gotten the 1 pi, and I have to go to 2 pi. 25 pi over 6 and 29 pi over 6, 18. Okay, there are my 6 solutions. And that was number 2 on station 9. So let's just take this as a moment to look at 2 sine x minus 1 equals 0. And let's consider the 0 to 2 pi solution. Oops, sorry. 3x. Okay, and let's consider all solutions. 2 sine 3x minus 1 equals 0. Oh, this isn't one of the stations. It's just something I want to be very clear and point out about, because it's exactly this thing that many students sort of really get confused on. So when I'm looking for the finite number of solutions, as I am here, just the solutions on 0 to 2 pi, that's the time when I have to go around the unit circle this many times. But in this problem, where I'm looking for all solutions, yeah, I only go around once. And then I add my plus 2 pi n, and then I divide everything by 3. Okay, in this situation, this is the one where I go around 3 times. It looks like we have a special guest today. Special guest. How are you? You're wondering, is it really? It's 6:23. Where are we going? I think that's a fabulous idea. You probably don't want to wait the other 6 stations. Well, fabulous students, I know how you hate it when I break these up into 2 videos, but guess what? When your life partner says it's time to go for a walk, the most important thing to do is to put down your work and go for the walk. I'll see you in the second part of this video.